We shall commence with the proceedings of our session today in about 5 minutes from now. Meanwhile, tea and coffee is served outside. You can have a fill of tea and coffee. All mobile phones put on to silent mode and be seated back in 5 minutes for the technical session. Today we have two sessions. First session is on technology and the second session is on raw materials and noble alloys. And we close the proceedings of this international conference with lunch. I'm sure you all so far have had two very nice, interactive, productive days with a lot of networking, fun, sumptuous food. And we would look forward to meet each one of you next year for the next session. Thank you. It's more before we commence with the proceedings of the session. We're really sorry for that. Thank you all for being here in time with us. Tea and coffee is served outside. You may kindly help yourselves to a cup of tea and coffee. Be comfortable, and we will commence in about 10 minutes from now. Thank you. Session of the Second International Ferroalloys Conference and first session on day 3. The topic for this session is technology. And I have the proud privilege in inviting our distinguished session chair, Mr. Srinivasan Iyer, Managing Director, Elkem, to kindly join us on the stage, please. A very warm welcome to you, sir. Mr. Srinivasan Iyer is Managing Director, Elkem. He joined Elkem in the year 2006. Also inviting our eminent speakers for this session, Mr. Shambagam Maniram, CEO, Tata Power DDL. A very warm welcome to you, sir. Mr. Ravit Hansraj, Control Engineer, Tenova Pyromet. A very warm welcome to you, sir. Mr. Tushar Galsasi, MD and CEO, Galsasi Smelting Private Limited. A very warm welcome to you. And Mr. Sangeet Jain, Director, Lanza Tech Private Limited. A very warm welcome to you, sir. So, ladies and gentlemen, calling this session to order, once again requesting for all mobile phones to be put on to silent mode. The topic of this session is technology, and the time duration is approximately 1 hour 30 minutes, which includes the opening and closing remarks by our session chair, presentations by all our eminent speakers for approximately 15 minutes each, and we shall have question and answers in the end after all the presentations are over. And may I now hand over to our session chair for his opening remarks and to carry forward the proceedings of this session. Over to you, sir.
We had a nice evening yesterday, and it's time to do some work. So we have 4 presenters here with 4 interesting topics, and the first one is from Tata Power. Let me introduce the first speaker. Mr. Manthiram Shenbu, Chief Operating Officer, Tata Power Delhi Distribution Limited. He's a hardcore power professional with 3 decades of experience in thermal and hydropower generation, distribution, international business development. Before joining Tata Power DDL, he headed the power business and retail distribution in Bombay. He has been a regular speaker and has presented various papers at national and international conferences on the subjects of renovation and modernization of hydropower plants. He is an alumnus of National Institute of Technology, Kurukshetra, and also attended the Management Development Program at Asia Institute of Management, Manila. We are very excited to hear you. Power is a big concern for the ferroalloy industry, and we welcome you to give your presentation.
Okay, fine. A very good morning to all of you. I was wondering, what am I supposed to speak today? All I knew was power is an important ingredient for most of you here. And I think many of the cases is close to 30% of your ops cost as well. So I just try to summarize where as a country we stand on the power sector as such, dominantly covering the generation and the distribution part of it, and most importantly on the tariff part of it, because that's very key to all of you. And where do we stand on the tariff, and what are the hurdles as of now, and how it can be resolved? So, yeah, most of these data is probably some of you are aware because you generate your own power as well. Nevertheless, I thought it's good to have a look at it. So if you take the demand and the supply part as a country, we have a peak demand very close to 182 megawatts. Now, having seen that, what's the base demand? It is 125 gigawatts. And if you are very familiar, peak demand happens mostly in the summer months, and it happens for a very few days. And how is the supply side? So as of now, the installed capacity is close to 360 gigawatts. And even if one wants to curtail the numbers with some of the stranded assets, it's nothing less than, say, 320 gigawatts. So what should be an ideal installed capacity? So typically, what we call it as a spinning reserve is it should be anywhere between 20 to 30%. And if you see many of the European countries, or let's take Singapore, for example, it structures in a way that as long as you have anywhere in the range of around max of 30%, you're well suited to meet the demand part of it. Now, having said that, we also have very close to 58 gigawatt of captive power. So I'm not getting into that, but it also shows how much the captive power takes care, as well as we don't have its PLFs, etc., but there is a huge potential lying there. And as we stand today, close to 77% is, I would say, base load or reliable power sort of a thing. And the intermittent power, I use the word intermittent power because when you go to wind and solar, the renewable journey part of it, we really have intermittent power, and since there is enormous focus there, that pie is slowly going to be higher and higher. It has its own challenges as the intermittent power is increasing, the way it has to be managed. We are just learning. Well, the whole world is learning. India is learning there too, and a lot of work has to be done there. And coal, as of today, while it is close to 60% plus, it dominates in terms of giving us the base load part of it, while additions are not planned in the coming years. But then, yeah, whatever is there to stay. Let's see what's going to come up in the coming years. I put a horizon of up to 2030. And what is expected is a peak demand of close to 340 gigawatts. And if that's the demand, is there a plan to supply it? So if you see we have a good plan of close to 830 gigawatts. Now, both ways, if you want to put across in terms of what will really happen on the growth part, as well as on the supply part, it shows we are pretty much there to take care of the demand part of it. Now, two important aspects I thought is we need to see at it. One is what is happening on the rooftop solar. And why rooftop solar? Because as a distributor, if my consumers become producer, obviously where will I sell? So we do monitor that part of the journey. And there are so much incentives to see that rooftop solar growth happens. And if that happens, how much will retail suppliers like us get affected? So there's a plan of 75 billion units coming up till 2030. And as the incentives rolled out by the government is increasing, and as the prices have come down even for smaller capacities, obviously in the coming years the growth will be plenty. And as Tata Power, we manufacture solar panels, rooftop solar panels. We are the #1 in India as of now. And we started this journey way back in the 1988s, and we see that there is tremendous opportunity here. Also, the electric vehicles are coming, and we are at the nascent stage at this point of time. There are projections what will happen till 2030. As you see, it's going up to 160 billion units. Now, maybe it's pretty optimistic. So even if you put down to half of it, so it's going to match the rooftop solar or offset the rooftop solar part of it. So in a way, the distribution companies should be happy that EV vehicles is there to compensate on the rooftop solar part of it. And if you see the bottom part of it, since we supply to Delhi, we just made a call for ourselves. If you take our base for Delhi, it's around 13,000 million units. And what would be the rooftop solar consumption versus the EV? There is, the EV is offsetting whatever is coming on the rooftop. So it's fairly a steady growth which will happen, and that should not trouble the distribution companies. So that augurs well for you in terms of how these companies would grow in the coming years. Now, I'll directly get on to the most critical question part of it on the tariff area to see what are the critical factors which typically affect tariff. And without any explanation, it's understood that given the residential tariff and commercial tariff in India, industrial tariff is higher compared to the residential part of it. Commercial tariff is slightly more than industry by, say, 7 to 8% on an average. So today, we see as a country we have close to 17.9% AT&C losses. And some of them are close to 10, 11, the southern states, whether it's Kerala or Tamil Nadu. And as you travel and go towards the central part of India, you have some challenges. Orissa is anywhere around 35% plus. So we have similar numbers coming up in Bihar as well as UP, which you are aware. But then where do we stand on some of the areas? If you see feeder metering, it's 100%. And metering is one component which is very, very important in case your losses have to be less. And if you see DT metering, we are still at 60% as far as the rural is concerned. And you go towards the urban part of it, it's still at 84%. So a lot of work has to be done there. And unless it is metered, the challenge of losses would continue to be there. The smart meter journey has started, early stages. Whatever benefits it would bring specifically for the industrial customers, wherein the monitoring happens on an hourly basis, on a 15-minute basis, it helps you understand your consumption better, so optimization chances are very high. So we at Delhi, Tata Power has started the smart metering journey, and we have installed close to 120,000 meters as of now. And we plan to put around 750,000 in the next 30 months. We have a capex approval as well. And our industrial consumers are the first to get those meters so that we can support them in the journey of optimization, make them understand their consumption as much as possible as well. So if you see the other aspect, there is a green component called ACS versus ARR. The average cost of supply, as of now, what is being shown is 37 per unit, but then probably it must be much, much higher, although I leave it at that number. But the point is there is a gap. Means as a retail distribution company, I do not get even my average cost of supply. So you are aware there are hardly a few companies in India who actually make profit on the distribution sector. And even on the paper, it shows they make profit. What actually happens is there is a component called the regulatory asset. And that regulatory asset components depends how big it is in different parts of the country. But then that is to give you a picture. Unless this ACS gap is mitigated, the distribution companies would continue to suffer. So these are national figures, and it would change as you go down to different state. So this is one area, unless this is brought down, it's difficult to bring down the tariff as well, because someone else pays for the cost. The other aspect, which many of you are aware, is the subsidizing versus subsidized consumers. All of you are subsidizing consumers, and in our sector, the subsidized consumers are the residential consumers part of it. Now, while the previous slide spoke about the losses, it doesn't speak about agricultural losses, if I may use the word. So the figures are there for you to see. These are all available on the net as well. So let's take Punjab or Tamil Nadu or Telangana, Andhra Pradesh. So very close to 25% is on the agriculture side, but on the revenue side, it's hardly anything. And you see on the right-hand side, the industrial consumers literally pay anywhere more than 80% of what the energy is served to them. So this is still not on the map. So if I add this to the distribution losses, it's for your guess to see where the number stands. And to give you an idea of the tariff part of it, there's a Delhi tariff, which if you take, for us, it's around 9 rupees, out of which 8 rupees is the base tariff, and the regulatory surcharge, which is what I shared some time back, the regulatory asset, 60 paise is what is being collected, and this is only the interest component. The principal remains there itself, and the 5% electricity tax. So if you take the base price of 8, 6 rupees goes towards the power cost, and 2 rupees goes towards the other charges, the overheads, and the maintenance of the entire distribution part of it. So the point I'm trying to share is that 6 rupees part of it, as it goes down, obviously the tariff goes down. And Delhi, the highest power is given to us, hence the average cost of power is pretty high for us. Probably that's assumed that Delhi consumers can pay, because the rest of the power goes to the smaller towns and villages part of it. But then if you see the tariff structure, the average domestic tariff is 6.3, less than 400 units is 5.6. The residential sales is very close to 45% in Tata Power DDL. Delhi as such is close to 52-53%. So a tariff of 9, average revenue earned is around 6 rupees plus. So that's where the rest of the cost goes on to the non-domestic, which is commercial, and the industrial part of it. So this component of subsidizing versus subsidized have to be addressed. We'll discuss a little bit as we go down. So the other part of the challenge is from a generating point of view. The plant load factors, what is being depicted here is close to 60%. Last year it was less than 60%, it's slightly better off. But then when generating plants are put, the thermal generating plants, if you have to break even, we all know anything around 80% is a must. So that the interest component is taken care and other expenses of O&M is also taken care. So when generation has a PLF of 60 plus, obviously that part of the sector is not doing good. So the figure also shows you where does the central stand versus where does the state stand. And the central is pretty good fundamentally because NTPC, the biggest consumer of producer of 50,000 megawatt, has its consumers defined, so it makes or augurs well for it. But the state ones do not have, and the private ones depends on how do they manage. Now, as Tata Power, we are a 11,000 megawatt company, 11 gigawatts. We have an average PLF of close to 80% plus, 80 to 83% plus. So our PPAs are tied up in a way that it manages. But then many of you are also aware what are we going through as far as the Mundra plant is concerned. But we have taken it in our stride and continue to see our loading is much better. But then there has to be work done to make this better, else the sector will have its challenge. And as you manufacture your own electricity, you're very well aware if the PLF is as low as 60%, how the cost goes up.
Mr. Chandan?
So, yeah, 2 minutes, yeah. So just to give you an insight of what happened this last 6 months, Delhi, if you see, there was a 2% energy growth, and in September, we have a 28% energy growth. So what happened where September consumption is more than July when it is extremely hot? 2 factors, the sweat factor, the heat factor was higher in September, but then many of you are aware that the tariff was reduced from August 1st, and it went as low as 0 for the less than 200 units. So the point is, if there is low tariff, obviously consumption is going to increase. And for Make in India, this is going to be a key factor. So unless it is worked upon, it's very difficult to... let me show the demand curve to give you an idea where do we stand on the demand curve. If you see the all India demand curve, the evening peak is so sharp. So unless we have measures to bring this down or flatten it, we'll have challenge. So there are 2 parts to it. How do we do it on the DSM, demand side management part of it, and how do we plan to meet this load? Through hydropower plants, peaking plants, or through pump storage units to help it. And the contributors, if you see all the 4 regions of India, the northern region contributes, the green one, much compared to the other part of it. So it's typically the summer load part of it which contributes. While I discussed on the PLF and the subsidizing part of it, the one factor which we have seen in our services in Bombay for the last 100 years and the last 17 years in Delhi is, as long as you have good service to the consumers, they end up paying you, your losses come down, and you become a very operative, benefit, profitable company as well. So in short, as long as the consumer services enhance, then many of these subsidized issue and PLF, everything will get addressed is our conviction. Thank you.
Thank you for a very interesting presentation about challenges in the sector. Definitely. So I introduce the next speaker, Mr. Ravit Hansraj, Control Engineer Tenova Pyromet. Mr. Ravit has worked as a software and hardware developer in a variety of industries before joining Tenova Pyromet in 2012. He is responsible for the development and maintenance of the Tenova Pyromet furnace information system, as well as the customization and implementation at various customer sites. He is experienced in the use of Visual C, SQL, QPC, charting and graphical interfaces, and Siemens PLC programming. Over to you, Mr. Ravit.
I don't see. So, yeah, these notes. Okay. Thank you. My name is Ravit Hansraj. I'm a control engineer from Tenova Pyromet, South Africa. I would like to thank the organizers for giving me this opportunity to speak. I hope you all find my presentation informative. The topic for my presentation is the benefits of Tenova's advanced AutoFurn furnace controller. Firstly, I would like to begin with an overview of my company's profile. Tenova is a global company comprising of business units around the world. These business units are divided into metals and mining divisions. We have 47 locations across 22 countries. The head office is in Milan, and I represent Tenova Pyromet, located in Johannesburg, South Africa. A little bit more on Tenova Pyromet. We are the leading company in the design and supply of AC and DC furnaces for the production of ferroalloys, platinum group metals, base metals, slag cleaning, and alloy refining. We design and supply plant equipment associated with furnace operations such as material handling, dust extraction, and furnace off-gas. We also provide feasibility studies, construction, commissioning, supervision, and operator training, ultimately offering clients peace of mind project execution. I'd like to move on to the topics I'll be discussing in my presentation. These include an overview of AutoFurn in relation to the roadmap we are following, some history, and future developments. I'll move on to the furnace information system, in which AutoFurn is now a small module. This will be followed by the core of my presentation, AutoFurn's electrode management and its control philosophy, including the automatic functions of electrode regulation, slipping, and baking. I will thereafter present some operational data captured from an 81 MVA furnace that we are currently commissioning. I will refer to this furnace as Furnace X. This data will be presented in AutoFurn's reporting feature and screenshots of AutoFurn in action. I will conclude my presentation with a video stream of AutoFurn controlling this Furnace X. I just want to start off with the overview of AutoFurn with a network interface and how the program interfaces with the furnace. AutoFurn is a Windows-based application residing on a server generally located in the server room. It is able to access PLC information through an Ethernet connection. The operator console is generally located in the control room, and the AutoFurn interface is rendered in a web browser as depicted on the right. I will go into more detail later on the interface. So an overview of AutoFurn and the versions that were created. Initially, version 1 started out as a PLC program as a simple logic controller controlling megawatts and electrode current As technology progressed, the program was moved into the Windows environment as a standalone application in version 2. This application inherited all the functionality of the PLC program, and these were enhanced over the years. The electrode resistance control developed was a breakthrough, leading to more stable furnace operations. Version 3 is the current version. It resides as a module within the furnace information system. This version has inherited all the functionality of version 2, along with some new developments. These developments include a web interface within the Tenova wide web development environment, which is also a Tenova product. The automatic slipping and baking functions and the automated reporting are also new developments. Moving on onto the furnace information system, we have developed a strategy with the following development objectives: to create a module-based system. This allows modules to exchange data using a defined protocol, and to allow a user to access the module through a common web browser, which is user-defined. This strategy was designed to attain the following advantages, where new add-on modules may be more easily integrated into the system. These will include future developments, for example, machine learning modules, and image processing technologies. A user may access the interface from multiple web browser-enabled devices, including smartphones and tablets. The system may also be customized to best suit clients by simply adding or removing modules. The furnace information system comprises of the following modules: the already existing AutoFurn, tried and tested. And in development, we have the mass and energy balance, which we wish to embed into the furnace information system. Currently, it's still a standalone program, but it's in development to move into the new system. We're also currently developing an ITAP system. This is meant to capture information at the post-tap hole and to track ladle information, consumables used at the tap hole, and lab analysis. The objective of this is to compile all this information into automatically generated reports so we can process this data and help optimize furnace operations. The historian is standard and has been pretty much moved over from a previous version. And currently in development is Pyromet Mobile, an application on the smartphone. This is useful for machine monitoring and machine control. And it is exceptionally good when commissioning a furnace where users need information to commission equipment. All right, so I want to move on to the electrode management philosophy. This follows the strategic objectives to automate complex operator actions, maximize furnace operations, and we believe this will ultimately lead to maximizing profits. The following advantages include decreased downtime due to fewer furnace trips, a decreased dependency on skilled operators, improved furnace stability, and increased metal quality and increased productivity. The following areas were prioritized to achieve the best results based on this strategy, and that includes automatic electrode baking, slipping, and regulation. So I would like to continue with the AutoFurn regulation control. AutoFurn implements deadband control, and the operator enters a set point as depicted by the green curve. And the operation variable in blue, in this case, it's the electrode 1 resistance, trends along. When the operating variable exceeds the deadband, AutoFurn will make a correction. In this case, as the resistance of electrode 1 is decreasing, AutoFurn will move the electrode up to make a correction until the resistance stabilizes. This information is captured from furnace X and has the following advantages. It has the ability to make real-time decisions, take simultaneous actions as opposed to an operator who has to create a single action at a time. It has dynamic settings, which are easily modified at runtime, and it guarantees consistent operation. The next topic I would like to talk about is automatic slipping, which we have currently working on Furnace X. This control algorithm uses the electrode paste temperature, the average position, some I² dt, and the electrode length burnt since the last slip. Deadbands are created around these operating variables, and AutoFurn is able to make a decision when best to slip. The daily reports are automated to collect all the slip information and all the current squared and megawatt hours per electrode, and is able to recommend a consumption rate to enter into the controller to best slip the electrode. The advantages we find is it's more reliable slipping. Operators no longer need to worry about this. They can tend to be forgetful and tend to long slip the electrode, leading to other issues. There's a decreased risk of breaks because you're baking the electrode correctly, you're slipping at the correct rates, and this leads to increased in productivity. The next automatic function that AutoFurn has is automatic baking per electrode. So in the case when an operator needs to long slip an electrode, this function will automatically bake the electrode to the defined millimeter slip, and AutoFurn controls this over the baking period, and we've noticed the following advantages. This includes improved baking, also a decreased risk of breaks, and of course, with the software managing this control, we see an increase in productivity, and it's currently working on Furnace X. Part of the package is automated reporting, which is quite useful for some clients. It's one of the areas we've been improving on in recent years. This report is generated from Furnace X in a PDF format. It can be emailed to any email address that's for the client. So there's 3 curves that we have a template that we'll be using. So this is just the first page. We have furnace power from the start of day till the end of day, the power set point, megawatt hours tap to tap, and electrode currents and average currents for the day. There are more variables, but I'm not going to go into too much detail there with respect to these types of curves. We also implement a shift report for furnace power per shift and some electrode information per electrode per shift. And from this data, we're able to process information to help us run the furnace a lot better. So the AutoFurn interface is within the web browser, as shown. It's in full screen, and I've captured this from Furnace X. So I'll just let it run for a while. The important information is in the title bar, per transformer, per electrode. The electrode regulation mode is set to resistance, and you can see AutoFurn move electrodes and the result of those actions. And at the moment, megawatt hour is set for automatic slipping. Automatic slipping is enabled, so electrodes are slipping at the rates based on the consumption generated from the reports. And this gives a good overview to the operator of what is happening on the furnace that AutoFurn is on and the settings AutoFurn is using. So we have our furnace power with a megawatt set point and the dead bands around that. And of course, electrode information, resistance, and current. the set point and their deadbands. On the right, we have electrode information, and this relates to Autofern's automatic slipping algorithm, all the parameters that are relevant. In this case, yes, the paste temperature thermocouples are not working. In this scenario, Autofern ignores it and treats it as undefined data, but the average position is working, and we are able to slip on a regular basis. All right. The next slide shows the automatic slipping page, the 4 variables per electrode that Autofern looks at, and the deadbands around the targets that we are trying to achieve. And the last slide is the baking schedule. It's per electrode, so you can bake all 3 electrodes at a time, and it's quite easy to use, and it's quite easy to track the results as well as the baking schedule is executed. And that concludes my presentation. Thank you.
Thank you, Mr. Ravit. I think as we go towards Industry 4.0, this is very, very important. I now introduce the next speaker, Mr. Tushar Galsasi. He is the MD and CEO of Galsasi Smelting. He joined the Galsasi Group in the year 2005, starting as an engineer projects. Since the last 13 years, Mr. Tushar is engaged in furnace design, engineering, innovations, R&D, project management, site services, and customer service for the ferroalloy industry in India and international markets. Currently, he is the director of the Galsasi Group, directly responsible for all the projects, marketing, electrode column, equipment, and most important, customer service. Over to you, Mr. Galsasi.
Thank you, Mr. Iyer. Good morning, everybody. I think I have a very interesting subject today of optimizing the furnace size for producing various ferroalloys in the same furnace. So in the subject what I have today, I'll cover topics of what are the most common challenges what the ferroalloy industry is facing currently. As a technology supplier, what solution we can offer to help to overcome these challenges. I'll run through some case studies in which we can see how we are trying to optimize these solutions what we are providing, and how in the end we as Galsasi are offering these case studies to come into reality. The most common question for any ferroalloy new investor currently, and this I have seen all across the world wherever I have traveled, is which ferroalloy should be produced. Now, ferroalloy industry is a capital intensive industry. So any investor who is wanting to set up a ferroalloy plant would like to have his return on investment as soon as possible. Now, this ties up probably with the unpredictable demand and supply of ferroalloys. It's practically impossible to understand what is a consistent demand of any ferroalloy. Now, I myself have been seeing this industry for 15 years. We have been in this industry for the last 35 years as a group. So to predict a sustainable demand and supply of any ferroalloy is one of the biggest challenges what even I see for now. And the most important is the fluctuating prices. Now, selling price of any ferroalloy is going to impact your bottom line. We have all seen the exponential rise of chrome market. We have also seen the dip immediately in the chrome market. We have seen similar fashion the silicomanganese market as well as the ferrosilicon market. And along with ferroalloy, what happens is your ore prices and the reductants also follow the same sequence of price rise depending on the demand and supply. Solution to overcome the challenge, indirectly as what we technology suppliers would like to contribute is, we should design the furnaces not only to produce multiple ferroalloys in the same plant, but we have to do so in a way that we can optimize the furnace rating using for all the ferroalloys. Now, Galsasi designs the furnace equipment and the furnace design holistically in a way that we can produce multiple ferroalloys in the same furnace. This approach of producing various ferroalloys in the same furnace may not be new in India. What I found it was practically new when we have seen furnaces in Europe or South America or even South Africa for that matter. So even though the approach is not new, Galsasi is moving a step further in optimizing the production of the secondary ferroalloy using the same equipment. When I mean secondary is that any submerged arc furnace, we design it for a primary alloy, say a ferrochrome. And now when we want to shift to a secondary alloy, that is the challenge, and what we are trying to overcome is to have the production optimized for the secondary ferroalloy in the same furnace. So we are focusing in terms of developing our equipment and technology in a way that we always right now design furnaces for producing ferrochrome, silicomanganese, ferromanganese, and even ferrosilicon using the same furnace. So our teams, our equipment, our design, and the core team from India, South Africa, and Europe are making this possible. In order to do this, we are focusing not only to maximize the production of each ferroalloy, but also we would like to reduce the cost of consumption for making the ferroalloy. The smelters what we are designing are able to operate at a wide range of electrode current densities as well. The new generation Galsasi equipment makes this possible. With our technology and designs for the ferroalloys, our customers have the flexibility to switch between multiple ferroalloys more effectively. So they can produce different ferroalloys, but they can do so by utilizing their furnace at the highest potential. I'll take some case studies in a way that we will support what we are trying to present. Now, the first case study is for ferrochrome production in a way that let us talk about how do we optimize the production of the secondary alloy. I'll take an example of building a 27 MVA furnace designed for ferrochrome. Ferrochrome typically is a high voltage operation, and the objective in this case study will be to produce the secondary alloy, that is the silicomanganese, at optimized production using the same furnace. So when the chrome market is down and the investor will see a sustainable increase in the production and the profit margins of silicomanganese, the producers would like to have the flexibility to shift from chrome to manganese. Of course, you will have some off-grade production to begin with. You may require some time to clean the material in the circuit. However, if the furnace and the equipment is not designed suitably for this flexibility, the producer has to compromise on the production of the secondary ferroalloy, in this case, silicomanganese. To give you an example, a 27 MVA furnace using old conventional designs and equipment will not be able to give you more than 16 to 18 MVA when you shift to silicomanganese production. However, by designing the furnace, its systems, and the equipment, we are able to load the same furnace when operating on silicomanganese to as high as 24 MVA production. Now, this gives us a minimum 5 MVA more production in the same furnace when you switch, and I'm considering a modest margin of 5,000 rupees per ton in the silicomanganese production. You can imagine there is a loss of earning of upward 4 crores if the switching is not optimized. So this case study was regarding production. The second important aspect what is beneficial is the cost, the OPEX and the CAPEX. Now, how are we going to do that? So the electrode column, as we all know in a submerged arc furnace, is widely recognized as the heart of your submerged arc furnace equipment. You can equate that to a motorcycle. Say a motorcycle, we call it a 100cc bike or a 200cc bike or a 500cc bullet for that matter. So the cost of equipment and the whole design dynamics depends on the engine CC. Similarly, in a submerged arc furnace, your cost of equipment and the entire design dynamics depends on the electrode size. So with Galsasi furnaces now, we can design a smaller electrode which saves on your capital investment as well as we can optimize the production by improving the power factor. To give you an example, a typical 27 MVA same furnace, I'll take an example. With old and conventional designs, the electrode diameter typically in India what we see is 1300 millimeters. However, using the new furnaces from Galsasi, we can design the same furnace at 1200 millimeter electrode diameter. On a similar example, for a most popular model in India, say a 9 MVA furnace, what we can design is that we can use a typical design of say 1050 what is available, conventional designs, but with our furnaces, we can reduce that to even 950 millimeters. In fact, we are constructing one ferrosilicon project in the Northeast for 11 MVA furnace using a 1000 millimeter electrode diameter. With the conventional electrode systems and designs, typically what I've seen in India is most furnace operators are worried to push the electrode current density to more than 5 amps per cm square. The main reason what I found was the electrode safety. But higher loads at reduced electrode diameters are possible if the furnaces are designed properly and are equipped with robust electrode equipment for sustaining the high heat loads. We are combining all these advantages in all our offerings, in which the flexibility is now with the producer to switch between a primary alloy, say ferrochrome, and switch to a silicomanganese or a ferromanganese operation, but with optimized production. Along with that, the new generation electrode equipment, it is designed for higher loads and higher heat loads. We have several examples over the last 10 years that the availability of the equipment is 99% plus. Now, higher power factor, of course, increases the furnace loads as well now because we are reducing the electrode diameter. This not only saves on your electrode equipment and the cost, but also helps to save the electrode consumption. And the most important point, a stable furnace operation for a wide range of electrode current densities. I'm talking as low as 4 amps to as high as 6.5 amps per cm square. In fact, we have projects what are running at 6.5 density in Europe consistently for the last 3 years. At Galsasi, we designed the submerged arc furnace, allowing the producers to produce multiple ferroalloys without compromising on the production and the operating conditions. Our customers not only enjoy the flexibility to switch between multiple ferroalloys, but they can utilize their furnaces at the highest potential, which is not possible in case of conventional systems and electrode designs. Every rupee saved in this very harsh and competitive ferroalloy market is what we always try to aim. And at Galsasi, we are really excited to provide proven solutions to maximize your furnace potential and for producing multiple ferroalloys in the same furnace to optimize the production for every alloy. Thank you very much.
Thank you, Mr. Tushar. It's a very interesting paper where you try to balance and be flexible. Thank you. Our next speaker is Mr. Sangeet Jain, General Manager and Director, Lanza Tech Private Limited. Mr. Jain is the General Manager and Director, Lanza Tech. He joined Lanza Tech in 2013 after having served 25 years at India Glycols Limited, a large chemicals manufacturing company with a focus on chemicals with a low carbon footprint and renewable resource. Look forward to your presentation.
Thank you, Chair. I take this opportunity to thank the organizers for giving us an opportunity to present what we are doing at LanzaTech. LanzaTech calls itself as a carbon recycling company. It was started way back in 2005 by Dr. Sean Simpson, founder of the company, and in 2015 we moved to US. Dr. Jennifer Holmgren, she is the CEO and she has been at the forefront of creating sustainable aviation fuels. We are based in Chicago. It's a suburb there in Skokie, and a lot of our people in the Chicago office, they do a lot of work on the synthetic biology. We have a large portfolio of patents. The company has been funded through private equity. Last year we completed round D funding, which was led by Mitsui, and even Indian Oil participated in that round, and they are on our board. We are currently in round E funding. What we believe is that for the human life, carbon is very important, and we need to find the ways where we can give carbon a second life, and that's something the company has always been focused on, how to get more value for the carbon and recycle the carbon that is available in various processes. What we also see today that energy is tending to be carbon free. You have many ways to produce power which can be carbon free way, but there are certain applications where carbon is the need. For a long time to come, aviation is going to be liquid fuels having carbon. We also need carbon for many chemicals and products that we need in our daily life. LanzaTech developed a process. The founder, he's a microbiologist by qualification, and he was looking at how he can help in mitigating the greenhouse gas emission impacts. And one way was to see if the gases coming out from the industry, whether they can be used to produce chemicals, fuels, which can be then used in our daily life. So we developed a process where we have a fermenter. It's a gas fermentation process, and it's a continuous fermentation where the microbe lives within a solution, and gas, which is rich in carbon monoxide, hydrogen, CO2, and the gas is fed to these reactors, and the microbes, they live on this gas, and as a metabolite, they give out chemicals like ethanol, which can be separated using conventional distillation processes. So the initial work that was done was by taking steel mill gases from the furnaces, and the process was developed using the real world gases rather than any synthetic gas. And we were able to show that this could be converted into ethanol. And then we put up pilots and demo scale plants to show that the process is viable. One of the things which happen when we convert these gases into fuel, one, they can be used as a transport fuel, and in the process we also end up producing biomass which has more than 80% protein content, and that can go into animal feed also. Another process that we scaled up was using this ethanol to convert that into an aviation fuel. Last year, Virgin flew one flight blending fuel produced by LanzaTech. We also are looking at various other products that can be made using these gases. The microbe, it can be modified to make certain, you block some of the pathways, and the microbe can be used to produce many other chemicals. once we had done this work on the gases which were rich in carbon monoxide from the steel mills, we also looked at what other feedstocks our process can handle. And some of the things which our process is able to do is when you gasify materials like agricultural waste or municipal solid waste into a syngas which is rich in CO hydrogen, that gas can be used to as a feedstock to our process and convert that into ethanol, which can again be used as a fuel or can go into making many more chemicals. These are the pictures from our first unit that came up in China. It's a Shougang Steel joint venture. The plant was commissioned last year in May, and it has been running for more than a year now and has produced more than 8 million gallons ethanol. So these are the pictures which show the process, the reactors, and the pipeline that you see. It's the pipeline from the steel mill carrying the gas to this unit. So what is the advantage that we provide? So many of these processes, they end up in the process of making steel or other ferroalloys. A lot of CO gets generated. The options are either you can flare it, which adds to the greenhouse emissions, or you can combust it to have use for power and heat. And our process provides a way to capture a lot of these molecules into chemicals, which can again be used if they are used to make products, then it gets sequestered. And otherwise, it's if it's used as a fuel, it's a new life to that carbon molecule. So the process when we started, it was with the steel mill gases, which were rich in carbon monoxide but didn't have hydrogen there. The molecule ethanol also needs hydrogen, but the microbe is able to generate its own hydrogen, and we found that it could produce the ethanol using that carbon monoxide. Now, if you look at the first equation, if you were to combust this carbon monoxide, you end up producing 6 moles of carbon dioxide. But if it gets converted into ethanol, you are producing only 4 moles of carbon dioxide. So you are reducing carbon dioxide production by capturing some of the carbon into ethanol. As we increase hydrogen in the process, what we realized that in cases where syngas can be produced using biomass and municipal solid waste, we can use this carbon more efficiently. The ethanol yields go up, and when you have a ratio of hydrogen to CO of more than 2:1, you also start producing some water as part of the process. And in one of the projects that we are doing at Indian Oil Refinery, where the hydrogen to CO ratio is very high, the microbe shows a capability to not only to consume carbon monoxide, it's also able to consume carbon dioxide. Almost like 50% of the carbon in the ethanol molecule, it would come from the carbon dioxide molecule. So it provides a way to utilize a gas which otherwise would have gone as inert into the atmosphere. What it shows is the process is very flexible and robust from a scenario where there is no hydrogen to a scenario where there's a rich hydrogen to CO ratio. The process is able to work and produce chemicals which can be used. The impact for taking these gases and converting into ethanol is if you replace gasoline by using this ethanol, you end up reducing the oil that needs to be dug out from the ground, and it helps in reducing the emissions overall. At one of the steel mill study, we did a calculation that if we the project could use 100,000 fuel equivalent to 100,000 cars per year, and you have a emission saving of about 80,000 cars. Now, in US, there's a company called Ametis, and they have an existing ethanol plant. One of the things that they are doing now is looking at the orchard waste in the state of California, and that will be converted into a syngas, and that will be converted, and then the syngas will be converted into ethanol. We've done the basic engineering for this project. We also ran a pilot in Japan where the gasification unit was converting the municipal solid waste into syngas, and we put up a pilot there, and that has run for more than 2 years, and we have been able to make ethanol out of that municipal solid waste. This capacity of this pilot was about 15 metric ton per annum and was using unsorted municipal solid waste feed. We were able to show that it can use continuously the gas produced and make ethanol. The reason why I show this slide specifically is it's one of the toughest feedstocks where the gas composition is continuously changing and a lot of impurities coming into the process. But we were still able to show stable ethanol selectivity and a stable gas utilization to convert these gases into ethanol. Right now, we are at various stages of design, construction, and commissioning of the projects. Our first unit started last year, as I mentioned, in China. We are working with Indian Oil. That project is expected to commission next year at their Panipat refinery. We also working with the ArcelorMittal Group, one of the facilities that they have in Belgium at Ghent. They will be putting up this project for which engineering is already completed. We also have with Svena in South Africa a unit based on ferroalloy gases that would be putting up an ethanol unit where the basic design has been completed. And Sekisui, which put up a pilot, now they are putting up a bigger unit the first one was a pilot, now they will be scaling up to a much larger unit, and they intend to then take it to multiple units for commercial application. So this is the ethanol which was produced from our first licensed unit in China. And we also produced using ethanol sustainable aviation fuel at our facilities in US. You can see in this picture Sir Richard Branson and LanzaTech CEO Dr. Jennifer Holmgren. She flew in this flight this was from Orlando to Gatwick last year. We also working with many companies who can convert the ethanol produced to different chemicals. So what this also requires is kind of capabilities that can lead to developing the technology and improving it. We continuously work on the micro stains that we have. We working on the reactor designs, making them more efficient. We are very strong on process scale-up and optimization, and our synthetic biology team has been continuously working to create new stains, new microbes to scale up the another chemicals and processes. The way it started was way back in 2005 when we first developed this ethanol at the lab scale, and then the first pilot came at New Zealand Glenbrook Steel Mill pilot, and then Bao Steel and Shogang, demo scale units were run at these two places. One unit in Taiwan. Sekisui, at Sekisui we had MSW based unit. We have facilities in Georgia where we do our proof of concept. And all this gave us a lot of data based on which we were able to scale up our reactor models, and we can predict what kind of productions can be achieved once we have a gas composition. This is a list of chemicals which are at various stage of development, and we have been able to produce them all in our lab. And some of them are already at a scale where we have either piloted or ready for piloting. And commercially, we are offering today ethanol and 2,3-butadienyls. One of the things that the company has always been focused about is how we can add value. The prices in the chemical industry, it's like a commodity, fluctuating prices. So we thought once we have steel in the ground and the feedstock is available, what else can be done? And we continuously have been working on the microbe. The first version was to produce ethanol. Then the next was to, can we produce another molecule in the same hardware? So we have been able to do that, and we have done for, we have developed acetone and IPA molecules which can be made in the same reactor. You just have to switch the microbe, and it will convert into a different chemical. So this allows the opportunity to switch over from ethanol if the pricing for ethanol is not good, or if you have an opportunity to make another chemical. So LanzaTech tries to bring the producers of feedstock to the users of these chemicals, and yeah, I'll be just. Yeah. So this is being driven by the consumer choices, where people are looking at sustainability. What we believe that the feedstocks for the future, they can come from the waste generated in our urban and rural areas. We don't have to live with this pollution. We can really use these waste and convert them into chemicals which are helpful, in our daily life. Thank you very much. And LanzaTech believes that recycling carbon would create a cleaner environment, and there's a technology which is available to recycle carbon now. Thank you very much.
Thank you. That was a very interesting statement. So-called biorefineries of the future. You can say that. Now, we have had 4 presentations, one on power, one on Industry 4.0, one on flexibility, and the last one on the biorefinery. I request the audience to ask any questions to any of the speakers. We have about 5 minutes more, so we can take about 3-4 questions.
Good morning to everybody, and good morning to the chair. Now, my question is to Mr. Hansraj. You know that in Ferroalloy industry, now automation is picking up, and as furnace operating people, we feel still some automation is required to know the length of the electrode without sounding the electrodes, without going for sounding the electrodes. That type of automation, if it is put in the hands of the ferroalloy industry, then a lot of production saving you will do. Is there any provision for that in your Fornestar?
At the moment, no, there isn't.
If you do come up with an idea, please let me know, and we can start a company together. And
Yeah, no. Previously, there was some development. By having the weight of the electrode, people converting it to the length so that it will give an idea. That was one thought, and it was going on, but it was not the full proof. So, a request for you will be some, good technology to know the length of the electrode without going for sounding of the electrodes. During sounding of the electrodes, what will happen? We will bring down the charge level, the electrodes will be lifted, and people will be measuring with the chains and all that. That is, even whatever higher capacity of the furnace, still this process is going on. Particularly, I know it is going on in India. So, if that type of sounding of the electrodes is known through automation, that will help the operating people.
well, yes, well, it's a problem all our clients are having. We don't have a solution at the moment.
Yeah, please try to do something in future.
There are efforts to use machine learning to try and work this out.
Yeah, Tenova, we have a lot of hopes on Tenova, which made a lot of things in ferroalloy technology. You please keep this idea and try
Yes.
to do something. It will be helpful.
This is
to
one of the
ferro-
problems we are striving to try and solve, but unfortunately there isn't a real-time solution other than a physical measurement or visualization of looking into the furnace exactly
Okay.
to find the length. But yes, it's something we need to work on.
Thank you. With the permission of the chair, I have one question to Mr. Tushar. Tushar, your idea is well appreciated, and it is innovative thinking. But going for high current density and a common electrode for different products, that is a debatable point still. But I can straight away tell what if high current density is there, your paste also should support for that. You know, in India, how many furnaces are using Elcam paste, and most of the other furnaces, we are going with indigenous paste only. So going for high current densities, how electrodes will withstand with our, indigenous paste, and all those things are to be taken into consideration. No doubt it is a debatable point. It is very much appreciated so that for changeover of products, it will be helpful. Whatever your idea is, very much appreciated. Thank you.
Thank you so much.
Good morning. I'm Ramesh Agarwal from Raipur. My question is to Mr. Sangeet Jain. What I understand from your presentation, that the ethanol can be converted from carbon monoxide, not from the carbon dioxide, right?
Yes, it can be converted from carbon monoxide, where carbon monoxide is the main composition of the gas. In cases where you have high hydrogen, like in a refinery scenario where you have less of carbon monoxide and more of hydrogen, there's a possibility to consume some of the carbon dioxide also.
So most of our emissions from the stake, the carbon dioxide content is higher than the carbon monoxide. If I may suggest that if you can develop a model for municipal corporations for burning the municipal waste, this is a problem all over India to dispose of the municipal waste. If this model can work out, for every municipal corporation, the municipal waste can be converted to ethanol. I think that will be more sustainable, and if you can bring out this idea, I think.
So we have been working with people globally on this, and like I mentioned in Japan, we already have run this at a pilot scale, and now we are scaling it up to our next scale. So we are in dialogue with people on this.
Thank you. Thank you very much.
Hello. One more question to Mr. Jain. Actually, I heard now, what is the minimum CO level content in the gas which can be utilized for this kind of thing? Is it above 50% need to be, or below, or what level of carbon monoxide at least?
So most of the cases in the steel industry and ferroalloy industry, they have very high percentage on the carbon monoxide. When we go to other cases where you have hydrogen as one component in the gas and CO2 as other components, we generally feel that if you have something more than 5% or 6%, it can work out.
No, in fact, we are using the off-gas for power generation. But we would like to certainly see whether power generation is better, or even then also we are not able to use 100% of the off-gas at times. So whether we can go for, it contains more than 50%, but around 50-55% CO level. Other components need to be seen. And how is the capex and opex for this kind of projects?
So it all depends on the
naturally,
scale. We can look at
Okay.
your
We'll
gas
talk
streams.
offline.
Yeah.
Thank you.
Yeah, good morning, everybody. I have one question to Mr. Tushar, that many of the ferroalloy operators are now small in nature and already are in place. So now they want to shift in between different products and all. So whether you have any retrofitting ideas and conducting some study and suggesting the best retrofitting arrangement to them.
So the subject is for new furnace as well as retrofits. So that we can look at it as a greenfield project, as well as we can study the existing furnaces and do retrofits. In fact, we have already done a few retrofit projects utilizing the subjects in the paper. So it is applicable for both.
Yeah, thank you. And one more question to Mr. Ravit, that many of the ferroalloy operations, they are a kind of audit kind of things. You are providing any services in India, I want to know. I mean, existing operations audit, I mean, what is the changes they have done something, and whether they are ideally operating conditions are there in place or any changes are required to be done. Are you providing any services like this?
Yes, Tenova Pyromet does offer those types of services, and we do feasibility studies quite often. So it shouldn't be a problem for us to arrange something to visit your site and execute that.
Okay, thank you.
Thank you. Thank you. I think we have finished our time, and I hand it over to the organizers. Thank you.
Thank you very much indeed, sir. And let's put our hands together for those very informative presentations we had in the morning. And I would request Mr. Iyer, our session chair, to kindly do the honors of presenting mementos to our eminent speakers as a token of gratitude. We present to Mr. Mani Ram, CEO, Tata Power DDL. Thank you very much indeed. To Mr. Ravit Hansraj. Thank you, sir. To Mr. Tushar Galsasi. Thank you very much indeed. And to Mr. Sangeet Jain. Thank you. Thank you, Mr. Iyer, for doing the honors. And may I now request Mr. Durga Prasad, Vice Chairman, IFAPA, to kindly do the honors of presenting a token of gratitude to our distinguished session chair of this session on technology. Thank you very much indeed, sir, for wonderfully chairing this session. And may I request a group photograph of the panel. And ladies and gentlemen, we now break for tea. The tea break will be of 15 minutes. I would request everybody to kindly be seated back in time for the next session. The next session is the final session of this international conference, and it is on raw materials and noble alloys. So looking forward to see you all back in time for the next session. Thank you. We would like to commence with the proceedings as soon as possible, as a lot of our delegates and speakers have flights to catch in the afternoon or the early evening. Raw Materials and Noble Alloys. And I have the proud privilege in inviting our distinguished session chair, Mr. Anup Gudgutia, Managing Director, Team Ferro Alloys Limited. May I welcome you, sir, to grace the stage with your presence. A very warm welcome to you. Also inviting eminent speakers of this session, Dr. Bhakta Hari Agasti, Chairman and Managing Director, Manganese Alloys and Reductant Consulting Company, WLL Carbon Traders. A very warm welcome to you. Mr. Xiaojun Chen, Analyst, Trafigura. A very warm welcome to you, sir. Inviting Mr. Naveen Dadu, Advisor, Peldon Enterprise Limited. A very warm welcome to you, sir. And also inviting eminent speaker, Mr. Ravi Shankar Marda, Director, Premier Alloys and Chemicals Private Limited. A warm welcome to you. So, ladies and gentlemen, the topic for the session is raw materials and noble alloys. The time duration is approximately, once again, 1 hour 30 minutes, which includes the opening and closing remarks by the distinguished chair, presentations not more than 15 minutes by all our eminent speakers, and question and answers in the end if the time permits. Our distinguished session chair for this session, Mr. A.K. Gudgutia, started his career with Aditya Birla Group, SL Mining Industries Limited in 1980 in Vapi, Gujarat. He established the Noble Ferroalloys plant for production of ferro-molybdenum and ferro-vanadium, which became the largest producer in India. He left the company as CEO of SL Mining Industries Limited, the ferroalloys division, in 1996, and started his own ferroalloys plant in the name of Boon Metal Alloys Corporation for production of noble alloys and ferromanganese in the year 1998. Team Ferroalloys was incorporated in Dadra and Nagar Haveli. Since then, the bulk alloys like silico-manganese, noble alloys, ferro-molybdenum, ferro-vanadium, power generation and code wines are added as total product profile of the company. He is the managing director of the company, and with his vision, now the Team Ferroalloys have become the largest producer of ferro-molybdenum in India. And ladies and gentlemen, I hand over to our session chair, Mr. Anup Gudgutia, to kindly carry forward the proceedings of the session with his opening remarks. Over to you, sir.
Hello. Thank you. I am thankful to IFAPA for giving me opportunity to chair this session. And I hope most of the delegates will be eager to go home after spending 2 days here. So, a lot of delegates have to catch their flight today, so we won't take much time and try to finish our session as per schedule. First of all, our first topic is met coke for ferroalloys industry with sizing. This topic will present by Dr. Hari Agasti. He is Chairman and Managing Director of MN Alloys and Reducting Consulting, WLL. Bhakta Hari Agasti is the Chairman and Managing Director of Manganese Alloy and Reducting Consulting, WLL Bahrain, Carbon Partners, representing Office Carbon Partners as AS Norway in Bahrain. Dr. Agasti has more than 29 years of experience in producing silicon metal, ferrosilicon and other ferroalloys along with greenfield projects, setup and commissioning in Middle East, India and Bhutan. He has specialized in using very reactive coal in production of silicomanganese, ferromanganese and ferrosilicon. Over to Dr. Agasti.
Thank you. Thank you very much. Good morning to everybody. Thanks to IFAPA for providing this opportunity to talk about thanks to Mr. Manish, and special thanks to Mr. Sandeep Goenkaji, whose idea is to present this met coal, reactive met coal, to the ferroalloy industry on this platform today. Thank you very much. So actually this is a very big, vast subject matter, metallurgical coal, reactive metallurgical coal for the ferroalloy industry. Because of the time constraint over here, I have tried to be precise, compact, and brief as much as I can, and as much a practicable information can be done on this platform. Because each coal, the coals for the different production of the different ferroalloys like silicon metal, ferrosilicon, silicon manganese, ferromanganese, is N chrome. They are all separate sessions. I was in Tangchung, China this year in 12 to 14 in China providing the silicon metal. It was almost 45 minutes to talk about that. But anyway, thanks once again. So this metallurgical coal, reactive metallurgical coal for ferroalloy industry with sizing. And this is actually, we have these Carbon Partners, is a 36 years old company being formed in 1983, and we have the offices in Carbon Partners in Kristiansand, Norway, one in Tennessee, in Knoxville, and now I'm representing in Middle East in Bahrain, which is my head office over there. And our partner, who is the NRCO, they have the raw materials from the Colombia. So I'll just go through in detail right now. So a little bit to talk about the Carbon Partners, and then the role of reductants in ferroalloy production, selection criteria of reductants, reactivity, SIO reactivity versus rank of the coal, reactivity of various carbon sources, and important properties of the materials. Then going to the characteristics of vital reductant components and how it is formed in brief. Then coal for manganese alloys, ferrosilicon, silicon metal production with sizing requirements both for Colombian and American coal, and the examples of high purity coal for silicon metal productions. And what are the specific advantages of using coal in ferroalloy industry in brief on that side. So as I said, I'll just go through this. Carbon Partners is almost 35 years old company providing the low-ash coal, charcoal, petrol, coke, wood chips, top-ranked in products, serving customers from 200,000 to 200 metric ton to 200,000, and this year we have gone 850,000 ton. And customer base is nearly all Western and Western world, providing very low ash coal, 1% silicon ash coal to the silicon metal industries. Specialties with the technical expertise, develop new sources, and offering special reductants with low boron and low phosphorus for the ferrosilicon, for the silicon metal industry in particular over there. So now this company has been taken over by Denmark, which is Bordeaux, a green carbon company, and they produce in Denmark the electricity by the wood pellets. This is just a Carbon Partners management people. If you see the other side, that's the Carbon Partners in Norway, and this side is the in Knoxville, and I'm here in Bahrain. So role of, basically what is a coal? Coal is a combustible rock, and it's a natural resource, is a source of energy. And every coal, there are so many coals and different types of coal, how to recognize the best reactive coal and to select, to give to optimize our production process over there. So basically, the role of reductants acts as a reductant in the kinetics of thermodynamics of silicon metal production. Apart from this, also a conducting and conducting for the electric current presses and ohmic resistance for the deep electrode penetration, which is very important operation requirement for the both silicon and other ferroalloy productions. So as you all know, just to give a small idea on that, which is how selection criteria of reductants, I'll just, this is called physical properties, petrographic composition, chemical compositions, SIO reactivity, free-swelling index, fluidity, and HGI, hard group index, of course, price for fixed carbon level, electrical resistance, and its environmental sustainability and supply security. So if you see how to select the optimal reductant based on a particular product mix, which is depending upon the ash content, chemical composition, SIO reactivity, of course the particle size, the free swelling index, which is called fluidity when at the higher temperature, how it transforms at higher temperature, and the volatiles and HGI, environmental sustainability, supply security, as you said. So if you see this reactivity, which is SINTEF reactivity determination, just to give you an idea how the different materials are placed on the SINTEF, which is a Norwegian measuring company in reactivity for almost all the reductants. If you see the charcoal, which is between say 300 to 400, 800 or 900, depending upon the types of the charcoal, and see the metallurgical coke from starting from 1500 to 2000, and the pet coke, of course, from 1600 to 2000, and coal starting from around 800 to 1200 maximum, which is the best reactive coal. And this is also the reactivity, which is dependent on the rank of the coal. So the rank is basically how the coal has undergone a transformation or qualifications under pressure, time, and that gives the metamorphism over there. So now, if you see from this, when the rank of the coal increases, some of the coal says the reactivity decreases. And also it has been verified in practice that if a coal is having the same rank, they also exhibit the different reactivity. It's not the same, but that is the metamorphism, the rank of the coal that says. So this is a little bit more elaborate. I'm not reading it out. It will be available to you later on. So you can see just what we just talked about, the reactivity of the different materials, carbon sources, which is very important for selecting a particular blend for a particular process. So we just talked about that high reactivity. The importance of the high reactivity is to obtain a high yield of the metal efficiency, and as low reactivity towards SiO affects the silicon losses, and also in other products like manganese losses and everything all over there. Hence, that means manganese in the form of MnO and silicon in quartz and in ferrosilicon in silicon in terms of silicon SiO. So high conversion, low amount of impurities, high electrical resistivity for overall good heat distribution. So reactivity and electric resistance of reductant have an important impact on the furnace power load and hence production capacity, furnace charge and energy consumption, as well as on the yield of the silicon process. So to increase the broadened resistivity, material with low conductivity are used, such as wood chips and other wood products. However, in some countries they are abundantly available, and in many countries they are not. So hence char and coal as a reductant is the most method of increasing the resistivity. The specification of product purity limits the number of reductants such as coal types that can be used in addition to the process that requires coals of certain reactivity. Because this cost of reduction material in silicon metal above 40-45% cost and energy cost in the production of silicon depending upon the location. So just to see how the coal characteristics of the vital reductant component and formation. If you see under millions of years, under time, pressure, how under the heat, how the plant remains goes to the peat, from the peat to lignite, lignite to coal, and coal to the different types of coal to the lignite, subbituminous, bituminous, and goes to the anthracite. So just the elemental analysis, coal which is given in a chemical formula over here. If you see on this, the low rank coal and high rank coal with increasing in moisture content, volatile metals, hydrogen, oxygen, nitrogen, and in anthracite you see when carbon is almost 90% above and very low, low moisture, but that is not a reactive material though. I'll come back on that in later part. So these are the coal components. What is a coal? That is coal is pure coal is fixed carbon, which is volatile matter, organic, which consists of organic plus mineral, and mineral matters is the ash. Ash is nothing else, is the non-combustible material, and the total moisture, which is also consists of the inherent moisture and the surface moisture. So this inherent moisture plays an important role in the reductant. For example, if it goes high, it becomes very friable, it doesn't react, and handling issues altogether over there. So I'm not reading out everything due to the time constraint. So I'm just switching to the coal for the, I'll discuss with the coal, two types of the coal. One is Colombian coal for the manganese and ferrosilicon and silicon, and one is a blue gem coal, the American coal for manganese alloys and ferrosilicon and silicon alloys. If you see the specifications of this Colombian coal, which is Pesolero coal, moisture around 10 to 12 and maximum 12.5. BM becomes age received 34 to 37, ash 1.5 to 4.5, and that can go to 4.5%, sulfur 0.5 and 0.8% max, fixed carbon 56 to 58, and minimum is 57%. And the good thing is HGI is only 45 to 48. That makes very compact and very good, not creating many fines in handling this. And also a free swelling index is a little bit lower, which is 1 to 2 as compared to the American coal, which is between 4 to 6. However, those two types of coal have different characteristics and they operate in the same to give you the result at the end. So sizing for ferrosilicon and silicon manganese for manganese alloys. So for the ferrosilicon, basically Colombian coals is 3 by 12 size mm for Colombian coal due to high surface area. Of course, you can use 10 to 25 by 30 millimeter, which has been used in the industry, but that because of the low swelling index, which is 1 to 2, this bigger size doesn't react that much as compared to 3 by 12. So the best for the ferrosilicon producers, which is in the Western world, they do 3 by 12. They prefer 3 by 12 or 5 by 15 over there. And for manganese alloys, like silicomanganese or ferromanganese, either 10 by 30 or 10 by 40 millimeter size Colombian coal is okay for the slag process. For the slagless process, 3 by 12 or 5 by 15 is the best, which has been proved over a long period of time over there. This is the same, I'm talking about the American coal, which is blue gem coal. Here is the moisture is low, 4 to 6 and maximum 6.5. BM is almost 36 to 38 and based on age received. Ash is also the same 1.5 to 4.5, but that can be under special conditions that can come down to wash to below 1% as well, specifically for silicon metal. And sulfur is a little bit high here in American coal as compared to the Colombian coal, which is 1 and to maximum 1.2. Fixed carbon is the same. HGI is again is a very good 40 to 46, but the important parameter for this American coal is the free swelling index, which is 4 to 6. That is a distinguished property of this American coal. That means you can take 10 by 12 both for the 10 by 30 millimeter or 10 by 25 millimeter, both for the ferrosilicon and silicomanganese, which I have done in Middle East for a long time, reviving a bankrupted company, which I'll share you in a little bit after some time. Sizing for the ferrosilicon, as I just said about this now, So now going back to the advantages of the coal. The advantage of the coal is very resistant material as compared to met coke and char, hence maintains a higher load per unit time, keeping the reduction temperature profile constant and uniform and higher productivity. Enables the electrode holder position to trend downwards all the time to utilize the energy efficiently for reduction process. Above all, the increase in the efficiency of the whole process, increase in recovery of silicon in ferrosilicon, manganese in manganese alloys production, silicon recovery in silicon metal. Acts as a substitute for charcoal in silicon metal production where there is scarcity of charcoal. For example, in Europe, you don't find much charcoal. So they use almost 80 to 90% with some wood chips over there. So this American coal, both American coal and Colombian coal have their own ways, and they provide the best result when it is used because of their higher reactivity. Some high purity coals, if you can see both, this is especially for the silicon metal. If you know, morely for the silicon metal, where for the solar industry, phosphorus and boron are the very important important parameters, because they hamper the solar energy absorption. So that is very important. So this American coal, as compared to the Colombian coal, provides very alternative 1, alternative 2. They provide very low for phosphorus and boron, which are very much interest to the specific silicon metal producers, and we have been Carbon Partners have been providing that for a long time over there. Hello. As a summary.
Agasti, you have another 2 minutes.
Okay, I will just finish it up. So the demand for the good reactive reductant is always there. A consistent high quality reductants ensure stable and efficient operating environment, as they lead to constant quality, increased efficiency by decreasing the overall cost of process. Also, the proximity of these very good reductants to the production unit decrease the overall silicon metal production cost as otherwise. It is also equally very important to have a safe storage ferroalloys, silicon metal reductants in different climates at a safe procedure to avoid spontaneous combustions. And important thing is FIFO and LIFO, fast in, fast out, last in, last out. I'll just move to this. These are all the how to store the coals on different climates, like minus 40 degrees centigrade in Siberia, in Kazakhstan, and everything altogether. So coming back to the conclusion, the reductant ferroalloys such as manganese production, different ranges. As per the practice, in particular silicon metal process, the cost is almost 18 to 26%. Depending upon the availability of the different reductants. So the cost will be optimized by optimizing the overall silicon metal process by opting and selecting the best reductant blend combination. Undoubtedly, this is because except the good thermal stability of quartz requirement, these reductants play a very important role in economizing the silicon reduction cost. So the cost will be again more supported if these reductants are very close to proximity to existing or silicon productions. Safe storage of reductants will vary from region to region, as I said, and that is very important as well to have a safe storage of the conditions. So now biomass, green carbon such as charcoal and wood chips will take a bigger role, and wherever it's scarcity, coal and char would be doing the needful. The supply of this best reductant for silicon production and the ferroalloys will be available, but probably at a cost following silicon and the ferroalloys indices. Thank you very much.
Thanks, Dr. Agasti, for your informative presentation on met coke for ferroalloy industry with sizing. Now, our next paper is China supply side reform and implication for coke market. Ziozun Chen, analyst Trafigura, will present this paper. Mr. Ziozun is analyst at Trafigura, a market leader in global commodity industry. As analyst for bulk commodity research, he is responsible for helping to shape the company's view on ferrous and coal market and macroeconomy outlook. with a particular focus on China. Prior to that role, Jiozun spent over 3 years in coal department of the company, covering responsibilities in operations, risk management and trading. Over to Mr. Jiozun.
All right, thanks everyone. It's a pleasure to be here at the International Ferroalloy Conference and to share some of our thought about the international coke market. We're going to start with a very brief overview of the general coke market. I'm sure most of the people are already familiar with that. Then we're going to review some of the recent market trends and experiences. I think it's important for us to understand what has happened and why it has happened, and it might give us a bit better insight on, to understand what's next. And then we're going to have to discuss briefly about the forward outlook on, especially on China's supply reform, and in the end, conclusions, and if there's any question. So the seaborne coke market in general is a very small market compared to, as such, for example, iron ore or coking coal. If 2018, it's roughly, the volume move is roughly about 22 million tons. So despite the small volume, it's still important. Well, on the supply side, it has been at least dominated by Chinese export, which accounts for about like half of the seaborne volume. But what's more interesting is that the demand picture. It's fairly diversified into various regions, which allows for a lot of dynamic market movements and a lot of arb opportunities. The seaborne coke market is also very much relevant in terms of when we're considering China and India's trade. So, for example, India buys roughly more than half of the coke import comes from China, whereas China export about more than 20% to India. Doesn't sound, well, it sounds less than 50% what India buys, but you have to consider as well, like India is probably the single largest country for Chinese export. And as we have already seen during the last 1.5 days, as many other speakers have already mentioned, we have seen a big divergence in China's steel production versus ex-China steel production in 2019. Doesn't work, okay. Which I think has really shaped the whole pricing and market this year. And briefly, basically, what we think has caused that, well, one, on the demand side, we have quite big momentum on the real estate sector from the Chinese market, which basically has helped the China steel demand to stay afloat, while basically the whole manufacturing sector has deteriorated, similar to other countries as Germany, Japan, or US. So manufacturing was weak. Therefore, like in general, the global picture has been weak, but China has sort of, been supported by the real estate, which is set to decline going forward. The central government has already announced capping funding into the real estate and not going to use it for further stimulus purposes. Okay, so, and a bit counterintuitively, the the recent supply reform has actually also helped to shape this divergence in 2019. So the supply reform, just briefly, came sort of in two different forms, in a sense. One is more long-term in terms of shutting down of the induction furnaces, for example, phasing out capacities, industrial consolidations. But there has also been like short-term disruptions in terms of production suspension in the winter period, but also, especially in 2019, more ad hoc suspensions for 1 week, 2 weeks, or a month, and also more targeted regionally than just a countrywide or basically focusing on bigger like steel production areas. So the cause of this is that we have a capped, like government is trying to cap the steel capacity overall, but allowing for steel capacity swaps, which basically has meant that in 2017-18, we have phased out inefficient units. We have been able to bring actually more efficient units online. So while the named capacity might have decreased, the production efficiency has actually improved. So which as well, like, while the demand is also healthy and requires a certain supply response, basically China has been responding in terms of more than 9% year-on-year steel production growth. So the supply reform was not only on steel sector, obviously. It has also affected coke production and coke sectors. So when you look at the big drop at the end of 2017, that was the first time when they started to suspend production during winter heating. That has equally affected blast furnace operations as well as coke battery operations. And this theme has actually carried on up until today. So what has this then cost for the seaborne coke market? Well, first result of that is there has been more volume concentration towards like closer destinations. So on the Pacific side, China volume starts to flow more into, has been more flowing into India, not so this year, but then flowing much more into Southeast Asia. And then on the Atlantic side, because Chinese coke was getting more expensive, was getting uncompetitive, and also with some quality issues here and there, then European counterparties, for example, has been looking for the alternatives, such as Colombian, but also sourcing supply domestically within Europe. And also relates to that, looking from the China side, we have had decline in Chinese coke exports. Well, and as you can, if you remember the chart before from the utilization, and you can see the volume actually happens to be dropping at the time when, well, logically, when they were capping domestic production. So it's both. One is price in terms of export competitiveness, but also second, it's just less volume available. And also a third implication, and probably more important for the ferroalloy industry, is that whenever in the past we had these like abrupt event of supply of production suspensions, then the price of coke breeze and nut coke tended to outperform inside China. Why is the, well, the reason, main reason of that is whenever there is a supply constraint, coke plants tend to screen less or not screen their coke and just sell everything lump sum domestically to steel mills. So basically then even capping the availability of coke breeze and nut coke. So here you can see the premium of coke versus not coke, for example, decreased drastically during that times. Okay, and so bearing all that in mind, and then what do we expect going forward? So first of all, on the supply reform agenda, we definitely going to expect further supply reform to be carried on at least until 2020, in particularly for the coke industries. Why? Is because we had actually a very strong execution on the supply reforms in steel or coal industries, but in general speaking, like coke industry, the execution has been relatively soft. And so it lags still a little bit behind on the overall central government target. So what we expect is that 5 major, coke, big coke production provinces are going to carry that load, which is Shanxi, Hebei, Shandong, Henan, and Jiangsu. And Shanxi is the biggest coke production province in China. We expect a little bit, domestic, like local governments protectionism in that regard. So while Shanxi has some nameplate reduction that it has to be done, roughly speaking, 15 million tons to 20 million tons, but at the same time, it is allowed to as well swap it against advanced production units. So net, the capacity reduction is probably not so significant. More importantly, for example, provinces such as like Jiangsu or Shandong, they are going to be more important in terms of net capacity reduction. Because, for example, in Jiangsu, as we have already seen actually last year, like Jiangsu has abruptly cut a very big portion of the coke production due to environmental reasons. But more importantly, I think it's just local provinces have just deprioritized that industry and wants to upgrade, in that sense, their industrial structure. And so what Jiangsu has done, we expect them to carry on in 2020 and to decrease, roughly speaking, another 9 to 10 million tons capacity. And then Shandong is probably going to follow suit on that as well, for environmental reasons, but also to align their target with overall coal consumption reduction that they have amended on within the 13th five-year plan. So with that being said, overall, we can probably expect that the coke capacity and the capacity utilization is going to be tightened up versus steel, despite we can probably expect some cyclical downturn in terms of steel demand and steel production, but overall, especially if all these execution are carried out in a short period of time, then that will definitely support the domestic coke industry and support their pricing power against the miners or against the steel mills. And what that means as well, when we remember the export chart before, we are probably going to expect that the export volume out of China are still remain at a relatively low level due to, again, domestic market paying the better price and also just limited availability. Now, how does ex-China deal with that in this context? So first of all, ex-China has been dealing with it quite well so far. Why? Because I think it's more demand-driven. We have seen that ex-China steel consumption and production has essentially shrunk this year. So it means on one hand you had less consumption, right? You didn't really need to consume as much as you did before. And second of all, and that's also relevant for the seaborne dynamics, is that a lot of the previously captive units or production that was expected to be produced for their own consumption has been freed up, and suddenly there is an excess of these units, and there is an excess of these like cargoes that's available and that's freed up in the seaborne market. And some of the increase in terms of, for example, the EU volume has had a big share in that. And so basically this has also...
Sorry to interrupt, you have another 2 minutes.
It's all right. So this has basically meant as well, like there's more supply in the short term available. Okay, and just to conclude, so we're probably going to expect, again, as I said, that the supply reform, at least from a China perspective, is going to be carried on until 2020. They have mandate to complete certain capacity reduction by end of 2020. Likely, the government, out of caution, could pull the agenda slightly forward by a few months. This will put further pressure on the time when they have to complete that. So this is expected to, again, tighten the availability from a seaborne perspective in terms of Chinese exports. Well, Nut Coke and Coke Breeze could even get more affected because when the Coke plants are sizing less or are selling domestically at looser terms, so they don't need to size. Well, ex-China, I think so far everything has been a little bit on a cyclical decline. We don't expect too much trouble in terms of balancing the seaborne market in this environment. But if we have pickup in demand later, and timing is important, and especially if we have a pickup in demand before the supply reform gets finished or gets relaxed, then we can expect some pressure on sourcing the right product, and especially if it's like localized pressure. Yeah, that's it. Thank you.
Thanks, Mr. Chen. Our next presentation is overview of the ferrosilicon, and the presenter is Mr. Naveen Dadu. Please. Mr. Naveen Dadu was associated with Bhutan from day first submerged arc furnace was commissioned. He has learned about submerged arc furnace, first calcium carbide plant of India. Today he is advisor to Peldon Enterprises Limited. Over to Mr. Dadu.
Very good morning, respected Chairman, Mr. Anupji, dignitaries on the stage, ladies and gentlemen. I, Naveen Kumar Dadu, advisor of Peldon Enterprise Limited, a major quality producer of ferrosilicon in the Kingdom of Bhutan, a country, a peaceful dragon which believes in gross national happiness. Am Damche Dem was the first lady to conceive and start a small induction furnace in 2003 to produce steel ingots. She, with her dynamic leadership, encouraged the Peldon family to grow. Her son Pema, our present MD, is a hard-working young entrepreneur of Bhutan, has taken the group to newer heights while preserving the tradition of Bhutan. Two more entrepreneurs joined hands with her, and today our brand, Perfect TMX TMT, production capacity is 0.25 million metric tons per annum. Peldon Enterprise started production of ferrosilicon in 2008 and increased capacity in 2009 by installing a second furnace. Our product has been very well accepted in the market, and we are exporting to India, European Union, Middle East, Bangladesh, and Nepal. Our motto is to be above the competition by maintaining high standards of quality and consistency of product. We lay special emphasis on doing business with integrity. Bhutan. Bhutan is a peaceful country which believes in gross national happiness. We talk about gross national happiness rather than gross domestic product. I won't emphasize more on the culture and nature of Bhutan, rather would like to inform you on matters related to the ferro-silicon industry of Bhutan. Presently, 2,300 megawatt hydel power projects are in operation. All the power plants are run of the river. Because of this, there is minimal environmental and social impact. Bhutan is a carbon neutral country. 72% of land is under forest cultivation, under forest cover, even though the constitution of Bhutan mandates only 60% forest cover. Environmental norms in Bhutan are very stringent, and all industries in Bhutan follow the guidelines issued by the Royal Government of Bhutan. Even Bhutanese individuals are proud of this fact. I never imagined myself will be associated with any type of ferrosilicon industries. I spent my childhood in Birlapur, where the first calcium carbide plant of India was established. And during that time, I developed a passion for calcium carbide. I started my career by selling carbide all over India. In all forums and conferences, ferrosilicon world capacity, demand and supply have been discussed and presented, including that of India, SAARC countries, ASEAN countries. The industry is worried about the current price of ferrosilicon, and few speakers expressed concern and their views on this. Mr. Iyer, the chairman of Elkem, last year, on this presentation here only, said, those who have knowledge don't predict. Those who predict don't have knowledge. So I will follow his advice and will not predict the future and demand supply scenarios or the price in numbers. Rather, would draw attention towards some of the real challenges being faced by the industry at present. In 1970, Chuka Hydel project was commissioned in Bhutan. A great visionary, Dasho Yugen Dorji, also known as Dasho, the chairman of Tashi Commercial Corporation, started a calcium carbide unit in late 80s. I also started selling their calcium carbide. He was looking for limestone for his plant and incidentally came to know that quartzite, a key raw material for production of ferrosilicon, is abundantly available in Bhutan. A dynamic person like Dasho immediately decided to set up a ferrosilicon production facility, and the first ferrosilicon unit was started in 1995. Dasho always appreciated my association with Bhutan Carbide and allowed me to visit silicon plant during the commissioning, and my interest in ferrosilicon thereon developed. In the year 2007, 1,020 megawatt Tala Hydel project started. Belden Industries Limited, formerly known as Bhutan Ferro Industries Limited, started production in 2008. 4 more ferrosilicon companies also started operation during the same time. So today, Belden Enterprise, Tashi Group of companies, and 4 more companies are producing ferrosilicon in the Kingdom of Bhutan. The main use of ferrosilicon is deoxiding steel, specialty steel and foundry industries, magnesium metal production, other ferrous alloys, and welding consumables. The current annual production of ferrosilicon in Bhutan is 0.16 million metric ton, and the industry follow the stringent environment norms of Royal Government of Bhutan. In India, the current capacity is around 0.10 million metric tons, whereas the demand in India at present is estimated at 0.24 to 0.25 million metric tons of ferrosilicon. It is expected that by 2023, an additional capacity of 2,220 megawatt hydel power will be available in Bhutan. Four new industrial areas are being developed. Bhutan is a landlocked country, connected only with road networks to India. Government of Bhutan is also welcoming FDI, foreign direct investment, in Bhutan. The governments of India and Bhutan are trying to establish a rail network to Bhutan very soon. Future demand of ferrosilicon depends on the growth of steel and allied industries. Steel and allied industries growth depends on growth of SAARC and ASEAN region and India in this region. Per capita steel consumption in India is approximately 68 kgs, whereas world per capita consumption is 225 kgs, and China roughly 590 kgs, and in Bangladesh is around 50 kgs. Considering the above facts, the steel consumption in India and neighboring countries should grow substantially. This will create demand for ferrosilicon in near future. Bhutan will be in a position to meet this increased demand for India and neighboring countries. The major raw material for production of ferrosilicon are carbon material, quartz and quartzite, iron, beside electricity. Now the real challenges for the industry. The adoption and upgradation of latest technology is very important to meet international environmental norms. This needs investment and continuous research and development. As in the future, environmental norms are going to be more stringent. The industry has to be ready and decide the time frame to shift towards proper green industry. Indian furnace consultants and designers must do proper research and suggest energy-efficient designs with minimum impact on environment. Government of Bhutan has implemented strict environmental norms. The industries in Bhutan respond very well and invested to meet the required norms. Second challenge is replacement of charcoal. Major ferrosilicon producers in the world are not using charcoal, except industries in India, Indian subcontinent, and few countries. Charcoal can be replaced by low ash, high volatile coal, or low ash medicinal coke produced from high volatile coking coal. This type of coal is available in northeastern part of India. Semi-coke can also be produced with the coal available in Meghalaya and Arunachal. The new mining policy declared by the Government of India recently, this industry should support the new entrepreneurs to start semi-coke production units and washeries to reduce ash in the coal. The industry should approach Government of India to allot specific quota in near future for production of semi-coke. The normal LAMC producers are facing problem of coking coal. The ferroalloy and the coke producers of northeastern states should approach Coal India jointly for allotment of linkage of coking coal, especially for coke industries producing low ash material coke for ferroalloy industries. Low ash high volatile coal of Nangal, Meghalaya, if properly washed, is a proper coal, can also be a good substitute of charcoal. In Europe, low ash high volatile coal from Colombia is imported and used in the production after proper washing and sizing. This is also possible in India. The trade war between USA and China had already affected global trade, creating uncertainties and negativity, which impacted opportunities of export. We can just hope there will be an end of the trade wars and negativity will be converted into positivity. Today's price of ferrosilicon is far below the cost of production. We all hope upward price corrections take place soon.
Sorry to interrupt, Mr. Dadu. You have another 2 minutes.
I hope in near future, global trade improves as subsequently demand increases and industry gets remunerative prices. I am very hopeful for the future of steel and allied industries, Ferroalloys Industries. Tashe Delek. Thank you.
Thanks, Mr. Dadu, for your nice presentation on an overview of ferrosilicon from Bhutan. Now, the last paper of this last session of this conference is ferromoly and ferrovanadium. It will be presented by Sri Ravi Shankar Marda, Director of Premier Alloys and Chemicals Limited. Ravi Shankar Marda presently is working as full-time Director and Secretary with Premier Alloys and Chemicals Private Limited since April 1998. He has about 40 years of experience, working experience in various industries in India and overseas. Over to Mr. Marda.
Which is the... Thank you, Mr. Gurgutia. Thank you, IFAPA, for giving me this opportunity to present this paper. To start the presentation, I'll first start with a very brief overview, information about our company. Premier Alloys and Chemicals is a leading and oldest manufacturer of ferrovanadium and ferromolybdenum in the country. Myself has been associated with the business, although I am a chartered accountant and company secretary by profession. This is a family business, and I have been associated with this full-time for last 20 years. We have been in this business for last 40 years and remain focused on only these two products. We supply to all major steel plants, small and big foundries within the country, and have been regularly exporting. Export is a flexibility and opportunity. We have been recognized by Engineering Export Promotion Council for our export excellence almost every year since last 10 years. So these are the types. So now I start my presentation on noble ferroalloys. I'm only concentrating on ferrovanadium and ferromolybdenum. So you see the picture of ferrovanadium on the screen. Then vanadium, we will try and go through overview of vanadium, then production, then we talk of demand, then we look at the prices, then we try and analyze the changes in prices, then we see what are the vanadium catalysts, its uses. We look at future growth, we look at Indian scenario, import-export of vanadium in the last 5 years in India, future outlook of vanadium in India, and then challenges being faced by Indian vanadium industry. Vanadium is a great soft, ductile metal, which improves tensile strength, weather resistance, fuel efficiency in auto and aerospace. It's mainly recovered from slag, which is collected from the processing of vanadiferous magnetite ore, where iron ore is the main product. Iron and steel is the main principal product. Vanadium is also recovered from fly ash, petroleum residue, alumina slag, and from recycling of spent catalyst. We look at the production, information of production. In 2017, the total world production of vanadium was about 92,000 tons, metric tons, V content. China was the biggest producer with more than 50% share. Other large producers have been Russia, South Africa, and Brazil. Vanadium is mainly used in HSLA, or we call it high-strength, low-alloy steel, which consumes about 90% of the world production. Vanadium is also used in alloys, superalloys and aerospace, about 4%, in chemicals about 4%, and in batteries and energy storage applications of about 2%. Then we look at the prices of vanadium since 1980. We choose 1980 since this was the year when we commercially started production of ferrovanadium in the country. If we see the chart of ferrovanadium since 1980 prices, there have been 4 peaks. There have been 4 peaks, major peaks of vanadium prices in the last 40 years. If we see the analysis, if I analyze the next chart, we see that the first price peak was in 1989 when the prices went up to $49.8 per kgV. It was mainly due to disappearance of Russian material, which started coming down once Russia restarted production. The second peak was in 2005 when the prices went up to $123 per kgV, which was basically advent of grade 3 rebar in China. Then the third peak was in 2008, very quickly after 2005. This was due to the problem of electrical power in South Africa, which is one of the major producers, and which resulted in lower production of vanadium and resulted in increase in prices. After 10 years from 2008, that's last year in 2018, we saw the prices of vanadium going up to $127 per kgV, which is more than the price hike of 2005, price peak of 2005. This was also again mainly due to the development in China, which had anticipated an increased rebar applications, coupled with structural deficit due to closure of high-weld steel in 2015 in South Africa. And also China has introduced a lot of environmental control, which restricted the production of smaller factories of vanadium in China. Now coming to current year, the prices have sharply fallen to $31 presently. Well, I think as Chinese saying, buy now or cry later, choice is yours. So why the prices have come down so sharply? This is mainly because of substitution of niobium on account of significant increase in prices of vanadium. Then the inventories started getting destocked, whereas the production also increased in China in the current year, first half of current year from January to June by almost 30% as compared to last year. Vanadium is also utilized as a pigment for ceramic industry. It's also used in production of sulfuric acid. It permanently fixes dyes to fabrics, used in production of petrochemical applications. Mainly about 4% of world production is used in chemical applications. Future of vanadium. Vanadium market is expected to grow around 3% CAGR 2019 to 2028. As I said in previous slides, steel remains the key pricing driver for vanadium because it constitutes almost 90% of the world vanadium consumption. New rebar standards in China, which is effective from November 2018, doubling to the rest of world standards, would also require increased vanadium production. Also similarly, VRFB batteries, consumption of the same is likely to expand exponentially by 4 times in the next 10 years. From the existing about 2%, they are likely to go up to 8% in next 10 years. More so, the substitution of niobium, which we saw last year because the prices went up very high, is likely to be very short term, and because niobium is 45% heavier than vanadium, and it's not very easy to substitute unless there are compelling reasons. Also, we understand that vanadium is one of the 34 strategic metal identified USA, which USA is consuming about 11% of world production, whereas they have hardly any of their own production of vanadium. Hence, we feel that the prices of vanadium, the future of vanadium which is presently in balance, is likely to be promising and encouraging. Now we look at the more interesting part of Indian scenario, which we analyze. Basically, in India, it's all being done in the small-scale industry. So the datas are not readily available. So we have tried to capture our own estimates based on our understanding and relationship with the various producers of the country. So India accounts for about 2% of our total world production. Ferrovanadium is produced mainly in India out of indigenous vanadium sludge, imported V2O5 concentrates, ammonium metavanadate, and V2O5 flakes. Domestic availability of vanadium sludge from alumina industry is very limited and insufficient to meet the domestic requirement of ferrovanadium. The gap in raw material availability is met by imports of V2O5 concentrates, including intermediary products like ammonium metavanadate and vanadium pentoxide flakes. India concentrates have been concentrating in the past for manufacturing 50% grade of ferrovanadium. But of late, there is a growing requirement of 80% grade, and now India producers are manufacturing both 50% grade and 80% grade of ferrovanadium. Most of the steel plants have been also gradually moving from 80%, gradually moving to 80% grade from existing 50% grade of ferrovanadium. So as I said, Indian manufacturers are mainly small, medium-scale industry, which in total numbers are not more than 10, which are spread over eastern India mainly, with one unit each in western and southern India. And in India, vanadium is manufactured by aluminothermate process as compared to furnace route internationally. We look at the data of import and export of ferrovanadium in India. We find that in last 5 years, we find that the ferrovanadium import has been increasing. It was also mainly because of the free trade agreement which India has entered into. From 1st January 2017, the import for ferrovanadium from South Korea comes under nil duty. So that is the cause of increase in ferrovanadium imports. And of course, export is an opportunity as like us. For the figures which you see in the export are mainly out of 2-3 suppliers who have been making export as an opportunity. Future outlook of vanadium in India is very encouraging. We feel the steel industry is going about 6 to 7%, where vanadium is mainly used. Indian steel production of finished steel was about 132 million tons, as against 104 million tons 5 years back. More so, the value-added steel, such as automotive, infrastructure steel, is increasing in the overall share of total steel production, which increases the consumption of ferrovanadium. And we also understand that the government is targeting almost 300 million tons of steel production by 2030, which will further give support to the vanadium industry. Vanadium is expected to grow from the present level of about 4,000 metric ton per annum to about 6,000 metric ton in the next 5 years. When I talk of 4,000 metric ton, this is based on 50% V content, that's the 50% grade material. So we feel that the future outlook for vanadium appears good. Like any industry, vanadium also faces challenges in India. The main raw material has been vanadium sludge, which is the byproduct of alumina industry, and has been now classified as hazardous material since April 2016 by Environment Ministry. So result is that the environmental cost is increasing, and it is becoming very difficult to get clearances for setting up a new plant. Availability of domestic vanadium-bearing raw material, namely vanadium sludge, is limited. Possibilities to increase. So the industry has to depend more on vanadium concentrate, catalyst from overseas, which has very low vanadium content and has unpredictable availability and also has process difficulties in terms of recoveries, etc. Also, another challenge we have is the duty-free import of ferrovanadium from South Korea and the free trade agreements, which is keeping the domestic prices below international landed prices in India. So this is what was about vanadium. Now we look at ferromolybdenum. You can see the pictures of ferromolybdenum, how it looks like, and also the moly oxide. In ferromolybdenum, we will look at the molybdenum overview. We'll try and analyze the production, look at global consumption, industry-wise demand, consumption, molybdenum ore prices, import-export figures for last 5 years in India, present molybdenum industry in India, challenges for moly in India. Molybdenum is produced and extracted from mine ore, both as a primary product and also as a byproduct, and is also extracted from scrap material recycled by China by chemical process and melting. Molybdenum is extraordinary metal in high demand and often used in applications like stainless steel, stronger alloy steel, tool steel, construction steel, which requires high strength at high temperature. It's also used in catalysts, lubricants, pigments, corrosion inhibition applications. We look at the world production for molybdenum in 2007 and molybdenum in 2017. The total volume was about 558 million pounds, which is equivalent to about 250,000 metric tons, MO. The main producer has been China, as usual. I mean, they're also the biggest consumer as well. China has about 200 million pounds of MO, which is about 90,000 metric tons, and constitutes about 36% of world production. Similarly, South America stood second place, which has about 190 million pounds of MO, which is equivalent to about 86,000 metric tons, and constitutes about 33% of the production. North America is in third place with about 130 million pounds, and balance is rest of world. We look at vanadium moly applications, molybdenum consumption in the various industries, but it comes to the steel industry accounts for almost 79% of the total consumption, and other industries like nickel alloys, chemicals, ammo metals account for about 21% of the applications of vanadium, of molybdenum, sorry. Industry-wise, molybdenum demand, we try to show here in this chart between how is the consumption of moly internationally in the world and compared to that in India, in the textile, aluminium, pulp and paper, food, tobacco, cement, chemical, iron and steel, others. As explained in the last slide, the steel remains the main area of consumption in molybdenum. We look at the prices of moly ore concentrate for the last 5 years, and we find that the prices have been, in May 14, the prices had gone up to almost 14.9. The peak was about $14.9 per LB, which came down to about $4.5 in July 15, and has been hovering between $11 to $12 per LB MO since last 1 year. It's very difficult to predict the prices, and it's anybody's guess. So we now look at ferromolybdenum industry in India and its future. Molybdenum in India constitutes about 3% of world consumption. Molybdenum has wider applications and customer base compared to ferrovanadium in India. Consumption of both ferromoly and moly ore in India has grown from about 8,000 tons to about 12,000 tons in the last 3 years and is expected to continue growing. Unlike vanadium, there are no real substitutes available for molybdenum. India is second largest producer of steel, and hence steel industry is growing at about 6-7% per annum, with focus on automotive, stainless, construction steel, amongst others, which would require more molybdenum going forward. Finished steel production is about 132 million tons and is expected to reach 230 million tons, going by the 8% growth expected, which we saw yesterday in the Tata Steel presentation, thereby providing a great growth potential for molybdenum consumption compared to other parts of the world. Then we look at here the figures of import and of moly ore, that's roasted molybdenum ore, and ferromolybdenum in India, and the export of ferromolybdenum in India. We see that in the last 5 years, while the roasted molybdenum concentrate has been increasing significantly, but the import of ferromolybdenum has increased much more than the import of roasted molybdenum concentrate. It is mainly because of the applicable nil duty, which was made applicable from 1st January 2017 under the free trade agreements from South Korea, which has created this supply demand, and more of finished product has been imported than the raw material. Yep. Last, and just only concluding very slowly. So we have following challenges in India: duty-free imports of ferromolybdenum, as I said, from South Korea. Then Iranian molybdenum ore, which was available to Indian converters at attractive prices, is not available presently due to the US sanctions on Iran. Unlike ferrovanadium, molybdenum ore is 100% imported. Molybdenum consumption is mainly run by small-scale industries, which are low capital intensive and mainly surviving depending on the price fluctuations, because the volumes are small and margins are very competitive. Quality consciousness of small end users are very less, giving scope of discounted aspects raw material and creating a threat for fair competition for manufacturers focused in conversion of standard quality ore. So I think thank you very much.
Thank you, Mr. Marda. And I'm very much thankful to all my speakers of this session. Now it's open for question answer. We will take few questions because we are already late. If anyone has any question. Okay, so I declare end of this session, and once again thanks to IFAFA and the delegates for participating in this session as well as the conference. Thank you very much.
Thank you very much indeed, sir. And I would request our session chair, Mr. Gudgutia, to kindly do the honors of presenting mementos to our eminent speakers as a token of gratitude. We present to Dr. Bhakta Hari Agasti. Thank you very much indeed, sir. To Mr. Xiaojun Chen, analyst Trafigura. Thank you, sir, for that presentation. To Mr. Naveen Dadu. And to Mr. Ravi Shankar Marda. Thank you very much indeed, sir. And may I request Mr. D.K. Mohanty to kindly do the honors of presenting a token of gratitude to our distinguished session chair, Mr. Anup Gudgutia. We once again thank you, sir, for wonderfully chairing this session. And thank you, Mr. Mohanty, for doing the honors. And may I request for a group photograph of the panel, please? So, ladies and gentlemen, with that, we are almost coming to an end to this 3 days Second International Ferroalloys Conference 2019. And may I invite Mr. C.V. Durga Prasad, Director, Nav Bharat Ventures Limited and Vice Chairman, IFAFA, to kindly do the honors of presenting the closing remarks and proposing the vote of thanks.
निकाल लीजिए लैपटॉप में निकाल लीजिए okay. Hello everybody. So it gives me immense pleasure to announce that the resounding success of the IFAFA International Ferroalloys Conference 2019, which has been made possible by your guests and presence. Over 460 people have attended, out of which 355 from Indian delegates and 75 from the international delegates from 30 foreign countries. Is this calls for a big clap or no? Thank you. So very informative and valuable presentations have been made during these representations, Balkan as well as Noble Ferroalloys, environmental issues in the ferroalloys industry. We take home these deliberations valuable conclusions. This is a great potential for India to become a major producing hub for the world, given the right encouragement by the state and central governments. Present installed capacities over 5 million tons could be fully utilized. From the present production capacity, after meeting the domestic demand, about 40% is exported. India has a large pool of skilled manpower, technology, and is capable of achieving the higher capacity utilization, creating a large pool of employment. We seek from this government exemption of import duty on the inputs and increase exports incentives to complete the international market. I would like to thank Sri Fagan Singh Kulasi, Minister for State of Steel, for sparing his time in inaugurating this conference and assuring the industry to extend full support. I would like to also thank Mr. Honorable Minister for Road, Transport, Highways and Micro and Small Medium Industry, Nitin Gadkari, for his video message and assuring the industry to extend full support. I would like to thank all the delegates for attending this conference in large number and making this a big success. I would like to thank all the sponsors for their gesture, and the generous gesture with the help in organizing to meet the requirement for the organizing this big event. I would like to thank all the speakers for their information and educating representation. I would like to thank Mr. Arvind Singh and all other members who is in their own way has helped the committee in organizing this event. I would like to thank marketing and media partners Stalemint, channel partners Ferroalloy and Net.com, supporting organizations like IMNI, ICDA, Indian Steel Development Association, Material Recycling Association of India for their support. I would like to thank the conference organizers Indipo, ITC Maurya Hotel and their staff, IFAFA staff, and all other volunteers for their full support and making this event a grand success. With this conference, I conclude. The lunch is organized as per the schedule and request the delegates to stand there. Thank you.
Thank you very much indeed, sir, for closing the conference and kindly proposing the vote of thanks. I'm sure it is being seconded by each one of us present here. With that, ladies and gentlemen, we close the proceedings of the Second International Ferroalloys Conference 2019. Once again, thanking all our distinguished chairmen of the sessions, eminent speakers, and above all, we thank all you delegates for your participation in making this conference a huge success that it was. May I request everybody to kindly give each one of you a standing ovation and a huge round of applause, please. Thank you very much indeed. And once again, IFAFA had a successful event organized. And on that note, I invite everyone to kindly join us for lunch. Thank you for being a wonderful audience, for your participation and for everything else. Have a wonderful day ahead. Good afternoon and namaskar.